Our next speaker is Dan Schiebler. As head of machine learning at Abnormal Security, Dan built cybercrime detection algorithms to keep people and businesses safe. Before joining Abnormal, Dan worked at Twitter. First, as an ML researcher working on recommendation systems, and then as the head of web ads machine learning. Before Twitter, Dan built smartphone sensor algorithms at TrueMotion. Dan, over to you.
Hi, I'm Dan. I'm the head of machine learning at Abnormal Security, and I'm going to be talking today about resilient machine learning systems, how to design, launch, monitor, and succeed with machine learning systems that are resilient to the kinds of problems that appear in practical situations. At Abnormal Security, we build ML products that help protect businesses against cyber attacks. We detect a variety of different kinds of cyber attacks by launching these ML systems into production. And we face a variety of different kinds of challenges, from adversaries who attempt to elude our systems to all of the natural challenges that arise in large-scale software systems, like businesses who have different data distributions, large-scale distributed systems that have many moving pieces with many engineers working to improve them that need to be kept into a proper performance. These kinds of challenges require that the ML systems that run on them are able to adapt to the different kinds of distribution changes and the different kinds of problems that appear, and through this adaptation, maintain a high level of performance. Operating an ML system requires thinking slightly differently than how we would think about operating any kind of static system. I like to think of ML systems as athletes, or perhaps like a boxer. So you can think about your ML system as a boxer. You may have trained a number of different techniques and core strategies, your jab and your right hook, that are equipped to deal with certain kinds of common challenges that appear in practice. Your ML system may have a certain kind of task that it's practiced again and again and again of how to manage that kind of task and perform well on. You can think of the training of your ML system as drilling against a bag. The repeated types of samples that you would feed into your ML models to demonstrate how these models should adapt to new data, to demonstrate how they should perform on each type of sample with different kinds of features and labels that demonstrate what the model needs to do, is core for getting the model into the right shape where it can perform well in production. However, the situations that a model is likely to face after it's launched are different from those that it might face during training. If the only way that you prepare your boxer for an actual fight is by drilling against a bag, you'll run into serious issues. You might get knocked out or punched out of the ring by somebody who doesn't stay still and move like a bag. And in the same way, your ML model is not going to only encounter situations that look identical to the kind of data that you present it in training. If you present with only clean data that has features that are properly processed, that has stable data distributions, a fixed set of different customers or companies or types of users who you're integrated with, and only show your model these types of situations that are very static and consistent, in a production environment, when distributions change and things happen, your model will face issues, just like the boxer in this painting. Let's go through a concrete example, or a little bit abstract, but more concrete than a boxer, to talk through what are the kinds of problems that your ML system might encounter in production for a very basic kind of model. So suppose your model's objective is to predict something about users, or perhaps something about user behavior, perhaps a user's engagement with content on a particular day. The types of features that you're feeding into your model into production are likely grouped into a number of different categories. For this particular example, let's suppose that we have user features, features that tell us something about the user that we're making a prediction over. Perhaps these are things like any demographic information we have about the user, representations of things this user has done in the past, information that the user has provided to us as part of the onboarding process, or other information that we've inferred about the user based on the information that they've provided to us. There may also be content features. If this is a model that's predicting the likelihood that a particular user will like a particular piece of content, or the probability perhaps that a piece of content will be offensive to a user, then there's information that's present in the content itself that's valuable to present to the user. This information might be things like text data or image data that we're inferring, often unstructured information that needs to be heavily processed before it can be fed into a machine learning model to generate a final prediction for a particular task, often processed by upstream machine learning models, which can present problems, as we'll talk about in a moment. The third kind of features are context features. This can be very important depending on the kinds of tasks. For instance, content features can represent things like what is the day, the time of day, what is the state of the world at this point in time. For certain kinds of financial applications, it can be useful to feed into the state of the world or weather or even Twitter sentiment in context features. But this can also be more banal things. For example, if you're running a particular model on multiple different places on a website, this might be information about which of the different places on a website this model is being run. So let's go through an example of how these kinds of features might look different during training and during production, and how a resilient machine learning system will need to be able to cope with these kinds of issues that might appear. So to give an example, let's say that our context features, these are the things that tell us about the state of the world, is served by a particular data center that sits in one part of the world, and whatever server is providing these features is running batch jobs or polling real-time systems in order to extract this information and then serve it to the model in production. Now, suppose on one day when your system is running perfectly fine, a hurricane comes and knocks out that data center. Now, these context features are no longer available. This data center might be down for a significant amount of time, during which time your model will need to be able to deal with the fact that these features are no longer available. There will be some kind of defaults that you've built into your system. Perhaps these are defaults that are in the data center or whatever server is operating that's no longer available. Or these are defaults that whatever caller is present and the context features provider notices that the server is no longer responding and returns a default value. Maybe this is an exception, maybe this is some type of flag. Either way, your model has suddenly gone from a situation where the data that it was being fed had the values of these features properly populated to data that no longer has those values properly populated. If your model doesn't have a way to deal with this, then it will generate very poor results. One option, of course, is to build your system such that anytime any feature goes down for any amount of time, your model goes off completely, and whatever feature it's providing disappears. Sometimes this is acceptable, sometimes this isn't, depending on the product. A resilient machine learning system needs to be able to deal with these kinds of situations, especially if it's serving a mission-critical project, such as something that's protecting users from cyber attacks, or even something that's driving immediate revenue purposes at the business's bottom line, such as ad recommendation or financial products. Another possibility is that one of your features are fed by an upstream model that also serves other use cases. This is very common with content features. It's very common in a large organization for a set of models to extract information from raw content signals, such as image or text, massage that with a heavy machine learning approach, and then provide the processed downstream features to other models. This type of model that sits upstream sometimes is kept in a single version, and sometimes it might be modified. Let's say, for instance, that you have some superstar engineer who suddenly shows up on whichever team owns the upstream model that provides your content features. And this superstar engineer has decided that they've got a much better way to build and deploy these content features. So they make a fix. Maybe this is a change to how data is pre-processed. Maybe this is changing the model entirely. But for whatever reason, this change now causes a distribution change that's being fed to your model. the features that are being fed in are no longer the distribution that was present before, but now a distribution is determined by this change, this new pre-processing or new model the superstar engineer has put in this upstream team. This is a distribution shift that's very common. It's very common for improvements to upstream systems to leak into downstream ML systems. A resilient ML system is able to deal with this. It's able to not get thrown too far off by distribution changes of any individual feature. To give another example, let's say that the user features that your model is operating on are served by a batch pipeline. There's some kind of asynchronous job that runs every day or week that massages all the information about users, converts it into an online store, and serves that data online. Now, let's say that you suddenly onboard a massive new customer, or your product goes viral, and the onboarding pipeline that would add new users into your system experiences way too much load. The amount of users that are flowing in are way too heavy, and the system falls over. And it takes a few days before people can figure out how to get it to scale. During that intermediate time, your user data may become stale. It may become several days old or even weeks old, depending on the way your system is set up. A resilient ML system needs to be able to deal with data of any individual feature becoming stale. As you can see, these are three situations that we wouldn't normally think of as things that we want an ML model to be able to deal with in a robust fashion. These kinds of situations include things like distribution changes to upstream features, data pipelines that serve the features that we rely on going stale, or even features disappearing entirely. Only by showing your ML model these kinds of situations during the training process can you equip your model with the tools. Can you get your boxer to know how to dodge and dip when it faces each of these different situations and rely on how to operate in an effective fashion. The easiest way to do this in practice is to recognize that these issues appear, and through a production readiness review process, assess and simulate how your ML model would react to these different situations. There are many techniques for getting models to be resilient, and I'm not going to talk about the technical details of the techniques, but I'm instead going to focus on the organizational processes that we can put into place to ensure that our ML models are able to improve on these different kinds of situations, how engineers are able to identify that these situations are a common part of any part of ML applications, and how organizations are able to ensure that nothing gets launched to production that isn't able to handle the most important kinds of potential issues. This is the heart of resilient machine learning. So in order to make improvements to any kind of machine learning system, it's critical to focus on the iteration loop, the way by which we identify what are the kinds of challenges that we expect to face. How do we build systems that are able to adapt to those challenges? How are we able to measure the ability of our system to do this adaptation? And how are we able to learn from these measurements? Going back to identifying these different kinds of system issues that are common to face in an online setting, what we can think about is how by logging each sample that any model sees online and identifying when these issues occur, we can then replay new models that we build and new system changes that we put into place over these historical situations that we've seen in the past. So in this way, each challenge that we face, each outage, each data overload, each kind of distribution shift that we observe are examples by which we can measure the performance of our system in production on these situations, assess how new changes to our system and new improvements to our ML models that we build and put into place can improve the performance on these situations, and then learn from this and be able to experiment and build better models that are able to handle these kinds of situations in the future. Certain model architectures that represent features through a number of different ways and utilize flatter representations of features as opposed to heavy interrepresentations are able to better adapt to these kinds of distribution shifts. One example we can think of how it's quite easy to represent certain features dropping out is simply to drop out these features during training. Most of the time, these kinds of issues that models are likely to face online, distribution shifts, features disappearing, or even features going stale, are not things that are tremendously difficult to build into a model training process. If we can identify what these kinds of features are, augment our data set in advance, and then assemble these as particular evaluation cases that we test our models against, we can build a system that is able to perform well in a production setting on each of these different kinds of settings. Similarly to how the best way to prepare for a boxing match is to spar with opponents who are going to throw the same kinds of combinations that you'll see in the boxing match, the same is true for training a machine learning model. Only by augmenting our data set and our evaluation sets with the kinds of situations that a model is most likely to face in production, are we able to face and adapt to these kinds of situations and build a model that's resilient to these kinds of problems. There are many different kinds of organizations that have different degrees of iteration loops for what the iteration loop for improvement can look like. Some organizations are able to iterate extremely quickly and tolerate a certain amount of failure. Sometimes the best way to determine if a particular ML system is resilient enough is to launch it and see what happens and see how it behaves at the next setting that we observe. This is the easiest and lowest effort way to do this true resilience testing. Just like the best way to train a boxer at the very end of the day is to have them do a few pro matches. Some organizations, however, can't tolerate this risk. Whereas it might be okay for a social media organization to recommend the wrong kind of content for a few hours on one day if things go really poor, for organizations that are involved in mission critical healthcare security applications, sometimes this isn't possible. In these kinds of situations, our iteration loop looks quite different. For online focused systems, our hair systems, as you might see, that's able to move much quicker, where we can have these kinds of tolerance for online errors. In systems that need to operate entirely offline, our Tortoise systems, if you will, it's much more important to be able to build this kind of offline testing capabilities, to be able to stress test our machine learning systems against these kinds of issues. The hare and the tortoise are two sides of how an organization needs to function when dealing with this kinds of resilience testing, whether it can be a little bit more lackadaisical about launching to production, improving as each issue comes up, or rigorously testing, setting out a PRR design, production readiness review, and design review cadence for machine learning models that accounts for the most common situations that are likely to appear. This is the two sides, in many ways, of machine learning engineering, the offline testing and online testing, or offline performance and online performance. It's critical for an organization to know where they stand in terms of how much they're capable of building offline or online. Now, it's truly the case that both the hare and the tortoise want to build offline as much as possible, because when you're able to build, always able to iterate faster offline, and offline iteration is safer. However, offline iteration is much less representative of what truly happens online. And there's certain kinds of learnings that are far easier to gather online than offline. So the trade-off comes down not to whether or not you want to do any offline testing, but the degree to which you're able to decide when you want to flip the switch to online testing. An organization must assess its risk tolerance in order to determine what kinds of testing is possible online versus offline. To talk through some of the challenges and differences that appear between these offline and online systems, I just have a couple of quick examples to describe why offline testing can be difficult in addition to being absolutely critical. One is the difference between how features are provided. It's quite common for offline systems to be served features in ways that are different from online systems. For example, many offline systems utilize batch feature joining. You may have a large offline data set that you want to run your model on. Rather than hit the online feature serving API for each sample that you're assessing offline, you may do a large join using Spark or SQL or Hadoop or any number of other types of tools to do this. Online, you'll be hitting an online API. And this could be different because this API may return slightly different values in slightly different formats. There might be different languages that are providing these different types of tools. So this presents a difference between how features and therefore the distribution that your model will experience look in an offline and online setting. We can get around this to some extent by attempting to log everything that's served online, exactly how it's served online, and assess our model's performance on these logs directly. However, these differences will always be present, and only by doing a full online launch can we assess down this last bit of discrepancy that exists. The sophistication of the tooling that we build offline in order to close the size of this gap comes down to the risk tolerance of the organization and how possible it is to do testing online. Another reason why offline and online testing can be quite challenging is the feedback loop that's present in online machine learning systems. As training data or the individual components that feed into features themselves are determined by the way that the online experience is structured. And this online experience is in turn determined by the machine learning model, whose predictions are then determined by these labels and features that feed back into it. This feedback loop is present in the online system, but not present in the offline system. This is a discrepancy between the ways the two systems exist. And there's degeneracies that an online system can get into that an offline system cannot. Again, only by mocking out the different kinds of online systems that can experience these degeneracies, logging everything that we observe, and back testing on what we've seen in the past, can we assess offline what performance might look like online when these kinds of situations occur. Even so, these situations alone are often not enough to determine exactly what will happen in the future. Every organization needs to use the best it can to look at what's happened in the past in order to determine what's happened in the future. But a Tortoise organization that needs to focus explicitly heavily on resilience and preventing the slight kinds of large challenges that may occur in the future. It's even more important to anticipate what these issues might look like before launching an online system. One last example for how a online and offline system can look different is just on the set of samples that the model will actually run on. It's quite common in many online systems for the set of samples that the model runs on to be very different than the set of samples for which we actually have labels. It's quite common for us to only ever receive labels in a tiny percentage of the samples that the model runs on. This occurs very much in click-through rate prediction systems, for instance, where the system's objective is to predict the probability that a user will click on a particular sample. Since we only have labels, the presence of a click, on samples that were actually shown to the user, this is a very biased subset of the full set of samples that the model needs to run on. This presents an offline-online discrepancy that's very difficult to assess entirely offline. When a Tortoise organization is faced with a problem like this, it's critical for the organization to figure out how to assess the performance of the model on this set of samples, on this big blue chunk of traffic that we have right here, via a sampling technique, things like importance sampling and distribution reconstruction that can be performed offline to assess what online performance would look like on that set of samples. A hair organization can focus more on online testing and iteration with a lighter emphasis on offline testing. Regardless of where an organization sits on this spectrum, the focus on resilient machine learning and building a resilient system requires an iteration loop that incorporates both offline and online components to test against each of these different kinds of challenges that occur. Build components into your systems that make it resilient to these types of challenges through training on the exact kinds of production issues that you would expect to see or have seen in the past. Measuring through replaying these types of production systems and types of production issues on your models, and learning from these challenges and from these measurements to make more changes and introduce more types of data into your training process to build better systems. Thank you.